Pratima, Faculty in Physics, Institute of Aeronautical Engineering, Hyderabad. Let me discuss the topic Davisson and Germer experiment, which is in your first module of Waves and Optics. This is an extension of my previous lecture named as de-Broglie hypothesis, where we have studied de-Broglie introducing the wave-particle duality in matter. And I have also given a glance at the experimental verifications by various scientists, of which Davisson and Germer was the first one. If you want to look back into my video, the link is given in the description box below. You can have a look at it. Let's continue ahead with this topic of Davisson and Germer experiment. In 1927, Clinton Davisson and Lester Germer, who were working for the Bell Labs, these two physicists performed an experiment. And the results of these experiments matched with the predictions of the de-Broglie's wavelength, which we have seen in my previous video. And this have won the Nobel Prize for Davisson in 1937, after 8 years of de-Broglie winning the Nobel Prize for his PhD thesis, which came out as a de-Broglie hypothesis. This winning of the Nobel Prize, people predict it as Davisson and Germer, but Davisson have shared his Nobel Prize with Thomson in his article, because he have taken the Thomson's X-ray tube principles in his work and was motivated by Thomson. And this support you can find in this particular link. You can even read the address of Davisson in his banquet speech at Stockholm. Moving ahead, what really is the initiation of the experiment? The verification of the de-Broglie experiment, de-Broglie's hypothesis, was not the aim for the Davisson and Germer experiment. Rather, he and Kunsman were studying the nickel crystal for the scattering angles. The reference of this paper is given at the last slide. You can have a look at it. And in order to study the scattering angles of the nickel crystal, they were trying to use a tube in which they were putting this nickel crystal. And this is a liquid air bottle. And here is the paper which gives you the essence of how it started. So you can see here, this investigation reported in this paper was begun, okay, as a result of an accident. So what is this accident is this. During the course of this work, a liquid air bottle exploded. So what happened is the liquid air bottle they have taken and they have kept nickel crystal inside it, and they have raised it to higher temperatures. And they have suddenly observed that it exploded. They have seen that nickel has formed oxide layer around it. They were trying to remove that oxide layer, but it was very tough. For a prolonged time, they have to purge hydrogen and anneal it to very high temperatures. And somehow they were able to etch the layer of the oxide from the nickel crystal. And what did they observe here? You can see a very interesting observation. What happened here is, if you see here, there are two sets of the curves for 75 volts of the voltage which is given for the bombarding of the electrons. So what happened here, the upper part is, this is for the curves which are taken for the crystals before the accident taking place. And the curve is very nice, right? It's very nice. This arrow mark shows the way in which the electrons are incident onto the target, and this point of incidence at the bombardment is directly proportional to this vectors of the scattering. And if you see this distribution in angle of the scattered electron, there is a complete change for before accident and after accident. what is happening before accident and after accident, and this particular after accident curves is the first time ever studied for nickel crystal, and they were astonished what exactly is happening here. They were seeing as if like here when they were taking a polycrystalline nickel crystal, nickel, it is as if like they are taking many small crystal for studies where they are impinging the electrons onto them. Whereas this is as if like several large nickel crystals if you take and impinge the electrons, this would be, they expected that this would be the distribution in angle of the scattered electrons. So they came to a decision saying that the intensity of the scattering from a single crystal would exhibit a marked dependence on the crystal direction. What does this mean? The intensity of the scattering is related to the crystal direction. So they took hold of this particular clue and started for the experiments which we are seeing now in our present topic, the Davisson and Germer experiment. So what is it? This is the cross-sectional view of the Davisson and Germer experiment. What is the cross-sectional view? You are seeing here a filament F, which is just a tungsten ribbon-like thing, and it ejects the electrons out through the gun, and the gun and the next elements all are like closed out of the field view. So they are in a view where, or I can say a volume where air is not allowed into, which we now call as vacuum chamber. Okay, so now this electrons are made to pass through the gun, and these electrons are made to fall incident normally onto the target. So these electrons which are coming out, they can be scattered in different directions. But the scattered, only the scattered electrons beams which can fit into this solid angle of the opening of this particular collector, which is nothing but you can call it as a Faraday cylinder. You know about a Faraday box that you might have studied in your intermediate. What is a Faraday box? So this collector is a Faraday box, I can say, which has two layers, the outer box and the inner box, and the retarding potential between the two layers is so maintained that it can collect only the rays which are scattered in an angle of 20 and 90 degrees. So whichever are the rays which are scattered below 20 degrees will not be collected into the solid angle of the collector. So in order to do this, you will also have to do one thing. The target has to be rotated in such a way that only the angles will fit, falling into 20 to 90 degrees will be coming into this particular collector. And we should also be able to understand that whatever the rays which are scattering with a velocity lower than the velocity of the incident beam will be excluded from entering into the collector. That means if the rays have to be collected into the collector, they have to travel with a greater velocity than the velocity of the electrons which are being incident normal to the target. Okay, so this collector can be moved so that it can be taken collecting all the angles, and there is an arrangement outside here so that it can move smoothly. And this collector is connected to a galvanometer which gives the current, taking the number of electrons into it. So what happens later? We will see what happens later. They have taken different studies taking from here the target, which is they have taken like 8 by 5 by 8 mm of target crystal, and they didn't just take the target crystal as it is, but they have taken a bar of nickel and they have cut it along the 111 direction plane like the 111 direction plane. It means like you might have studied these are the set of the Miller indices for any particular crystal. You will have a set of planes, and all the similar planes which are parallel to one another, they can be treated as a family of planes. So this is such a family of planes, and you can cut it along 111 planes. How will you see it is like they can take the optical reflections of the planes, and they can recognize which plane is it. So this 111 plane, when you look from the top view of the nickel crystal, it will be a triangle in shape, and they have cut it, and they nicely cut it in the sense they have just taken a jeweler's saw and they didn't take any modified setup, and they just made holes around the edge of the crystal which is cut, and inserted some nickel wire into it so that it will be steadily fixed. And yes, they have raised the temperature of the target so that no recrystallization will take place. Very carefully they have done this. So with all this, yes, there is one point here. Even though they have taken care that 111 crystal faces only will be shown up, there are even 100 crystal faces even. But our main focus will be on 111 crystal plane. Okay, so now let us move ahead with this particular cross-sectional view and of the Davisson and Germer experiment. Moving ahead of several observations, these I have collected only 2 graphs for you, which will help you to understand the concept ahead. So this is a graph which shows the bombarding potential with the collector current. Okay, you're giving different potentials, and the collector is collecting all the electrons which are scattered. So for the different collector currents and for different angles of the scattering, you can see here the graph. Okay, so in the graph, what are you seeing? Suppose you can see here around 55 volts. Around 55 volts, there is here a maxima. So the way you have to study this graph is like, for the bombarding potentials at 55 volts, the exceptional intensity is at the co-latitude angles nearer 50. Okay, that's how you will have to study. And this is a major observation of Davisson and Germer. So please try to understand that it is at 54 volts that they were able to gather a highly exceptional intensity. Moving ahead, there is one more beautiful graph. Here you can see, as I've told you, 111 set of planes are there and 100 azimuthal planes were also there. Let us just keep 100 plane aside. Taking the 111 plane, which was of main concentration of by Davisson and Germer, you can see here for different voltages, applied voltages, you can see a spread of the azimuthal angles. So what is happening at 40 volts, they have reached a slight hump. They started a slight hump, and if you, this is the 40 volts, and if you see, it was around 60 degrees. And you raise it from 40 to 44 to 48 and then 54. What happened at 54? See, this is at 44 and this is at 44, this is at 48, and see here it is at 54. It reached maxima, and this 54 volts, if you extend it, it will hit the co-latitude at 50 degrees. So the maximum scattering angle is at 50 degrees. And now if you still more increase the voltage, you have observed that, you can observe here that the spur have decreased. Okay. The hump developed into a spur, and the spur is decreasing down to a hump again, and maybe it will reduce down to a simple straight inclining curve without any hump even, which started at 40 volts. So this is how the angles of scattering, the maximum angle of scattering is observed at what voltage is gathered. So what is it now? At 54 volts, you have got a scattering angle of 50 degrees. Okay, so now moving ahead, holding on to this particular data, we can see how the Davisson and Germer have proved the de-Broglie hypothesis. You might be confused. What is this cross-sectional setup? This many graphs? How can we? How can we cope up? But this is just my approach to let you understand what really Davisson and Germer have done in the Bell laboratories. The real cross-sectional view and what really the graphs they have taken support of. Now, come along with me. I'll show you how to answer this question in your examination perspective, point of view. Okay, so in your examination point of view, first you have to describe the schematic diagram of the experimental setup. How is it done? First, let me take, it will be an evacuated chamber. It will be an evacuated chamber where you will have a filament which is connected to a very low tension battery. This is a filament F, and once it is connected to a very low tension battery, it will emit the electrons. The electrons beams will be coming out. Now this electron beam have to be filtered with rather greater velocities so that they can go and hit the nickel crystal. This is the nickel crystal, which is the target. Of course, this was also there is also a setup to rotate the nickel crystal so that all the rays from 20 to 90 degrees will be collected. And in order to gather the ejected electrons from the filament with good intensity and a fine beam of electrons, we use a cylinder kind of thing with pores, I can say like pores here, so that it will give you the electrons like this. And this is subjected again to a battery, and which you can give like this. So this will drive this, this will act as an anode, attracting the electrons towards it so that it will pull the electrons and bring out a very fine beam of running electrons. Okay, so now what will happen? The electrons are coming and hitting the planes of the crystal. And as you know that if you take the atomic planes, every plane has its own direction, right? Every plane has its own direction. So once the electrons are hitting like this, this is different and this is different, and for this particular thing I can call, if I take like this, this is different, right? Of course, this and this will be the same. So the angles of the incidence are different. So the angle of scattering also will be different. So these electrons will be scattered at different angles. So these scattered electrons have to be collected by a collector C. So this collector have to be in turn connected to a galvanometer. So if this collector has to be moved from here to here, collecting all the rays which are coming out, you need a graduated circular scale. So this will be moved to note how, at what degree you are collecting the electrons which are coming out. And this collector is collecting the number of electrons which are coming in. That means it is giving you directly the intensity of the scattering, that is the scattering intensity of the electrons from the nickel crystal. So this is all about the experimental setup. Try to understand it, don't by heart it. Try to understand it and explain each component in the form of a sentence. It will form a very nice paragraph. Now, what is happening to these particular electrons? You can take this in terms of your Bragg's schematic diagram, Bragg's law. You all have derived the Bragg's equation, which is n lambda is equal to 2d sine theta. What is theta here? It is the Bragg's angle. What is Bragg's angle? If these are the number of planes, and if I take like this, the planes, if I take one electron beam coming like this, and it makes some angle with the, if this ray makes some angle, then what will happen? With this particular plane, it makes some angle. Let me take it as theta, which is this theta, the Bragg angle, and this will be reflected. So this is the incident electron beam, and this is the reflected electron ray. So what if you recollect back, there will be such rays incidenting on each atomic plane, and these will act as waves, and they will interfere constructively, forming constructive interference, which will lead to a maxima on your X-ray sheet, right? So recollecting that, you have got n lambda as the condition for the constructive interference, and 2d sin theta is the path difference between the two rays. Now, if I take this, recollecting my previous slide, when did we get the maximum intensity? At 54 volts, we got for the scattering angle as 50 degrees. Okay, so if this is 50 degrees, which is, I can call it as, yes, let me take it as 50 degrees alone, then this will be how much? 25. And 2d sin theta, you now need to find out theta. Theta means, so now if you have to find out theta, then you need to, let me show you nicely. You need to take this particular angle as, if this is 90 degrees, then theta will be equal to 90 degrees minus 25. So this will be equal to 65 degrees, right? So now if I start my derivation part, you take what? N as 1, the maximum order of diffraction, because here at 54 volts, you are seeing the maximum intensity at the 65 degrees of scattering angle. So I can take the order of diffraction as 1, and lambda is what you need to find out, and 2, and D. D is nothing but the interplanar spacing. There is library for each and every crystal. So D for nickel is 0.91 angstrom. D is 0.91 angstrom into sine of what is theta? 65 degrees. So if you calculate this, you will get around 1.67 angstrom, approximately 1.67 angstrom. So now what is this? This is according to Bragg's law. In Bragg's law, what are you doing? You are conducting an experiment, seeing the observation where you are getting the maximum scattering angle and the maximum intensity. So you can call it as an experimental result. You can call it as an experimental result. So now if you take the theoretical result, what is the theoretical explanation till now? What do you have for the electrons? You have in your hand the weapon, which is the de-Broglie's wavelength, lambda. Lambda is equal to 1.22 by root V, or else I can write it as, sorry, this is in nanometers. Let me write it in angstrom because I have taken the D in angstroms, 12.26 angstrom. Okay, so this one 12.26 by root of 54 angstrom will end up saying like 1.65 angstrom. Or else you can even take it like h by under root of 2 me, where h by under root of 2 mev. What is V? You know what is V, which is again the 54 volts, and you should take h, the value, the Planck's constant, m, the mass of the electron, and E, the charge of the electron. And if you substitute all of this also, you will end up in 1.65 electron volts. So thus, the theoretical and experimental results are arriving at the same answer, which means that the dual nature of the electron is agreed here. So thus, Davisson and Germer were able to prove the explanation of the de-Broglie in an experimental way, observing the scattering angle at 50 degrees, taking the parameter of the crystal of the nickel crystal. So here, thus, what has happened here is the de-Broglie's hypothesis has been proved examining experimental observations and comparing with theoretical formulae. So this is the conclusion of the Davisson and Germer experiment, and these are the references for you. In addition to your textbooks, you can even refer to this, so that this will give you an insight of what really have happened in the Davisson and Germer experiment. So this is, I have just added this so that you can get the evidence of whom is given the Nobel Prize. You can even gather knowledge of how the Nobel Prize is given, how the nominations are made. That's a general knowledge thing. And this is the paper which gives you the initial experiments done by Davisson and Kunsman on the nickel crystal where the accident have taken place. And this is the paper which gives you all the stuff needed for this particular experiment, that is this particular question. If you read this paper, you will get very, very vast knowledge of the experiment again, because they have done lot of experiments and observations based on this particular minimum fundamental observations what I have explained. And this paper shows all of them. Wishing you all the best, and I hope I'll meet you in my next video lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.